Welcome to our lecture. I believe this is lecture 11, but if I'm wrong, I'm close, and that's all you can expect in statistics. We're going to do a little bit more investigation of normal distributions, and then we're going to talk about confidence intervals. And I could tell you the chapters if I had access to our course website, but I don't at the moment. So confidence intervals. That doesn't look like the word intervals. Okay. So let me actually start with this picture, because I think this picture is pretty useful when asking questions about normal distributions, and your quiz will have this on there and you will be expected to use it. So it's a good idea to practice using this. Why is a graph a good way to think about continuous probability distributions? Anybody remember? Because probabilities are areas. And looking at a graph is a really nice way to find areas under the curve, especially when the picture helpfully gives you what percent of area is under each of these, right? So this 19.1% means that about 19% of the total area is between the 0 and the 0.05. If I want to find the percent of the area that's less than -2, I would do the 1.7 plus the 0.5 plus the 0.1, right? Where that 0.1 really covers everything less than 3 standard deviations. So I can ask some questions about this. For ease, I'm just going to use this one here, but you can do it again yourself, or you can ask slightly different ones. So first of all, if I had a sample whose sample mean was 215, so 2.15, sorry, based on this scale here, is that visually indicative that there's something interesting going on with the sample, or that the sample is not representative of the probability distribution? Talk about that with your neighbor. Decide if a sample whose mean is 2.15 is or is not representative of the probability distribution, and your logic for coming to your conclusion. Okay, anybody have any thoughts they want to share?
I was saying that I don't think that it's represented because it's so far to the right, and like normally in a normal distribution like this, lower is again, and would represent the majority, but that doesn't seem to be the case.
I agree with you. So our response was, in case you didn't hear, that this sample is probably not representative because the mean of that sample lives way out here, right, which is pretty far away from where you expect it to be, which would be right at 0. Right? The expected value of any sample should be 0. And here we have a sample whose mean is way out in this area, which indicates that probably most of the observations were way out in this area. And so you're like, well, what happened to everything else? And as a statistician, what that tells you is, oh, there's something interesting about that sample. Maybe my collection methodology was bad, but if we did a good job setting it up, it means maybe there's something interesting about this sample that I'm looking at, and it's worth looking more closely. If we did an actual calculation, we would see that the probability of being more extreme is only, let's see, in terms of decimals, I'm going to convert it to decimals, 0.017 plus 0.005 plus 0.01, which is 0.026, I think, 023. All right, a very small probability of being more extreme than that observation. And even if I said, well, let me make it symmetric and include this side over here, right, making it a little harder on myself, I'm still at less than a 0.05, of less than 5% chance. So that extreme observation makes me think that there's something interesting about my data, which means it's not representative. Because data that is representative is boring. It's not bad. It's just like, okay, that's what I thought. Move on to something new. That make sense? All right. This is working well. I like this thing. Can you see the annotations okay? Well enough? Okay. All right. How about this next question? What's the probability of observing a z-score, which is the same as a standard deviation step, between -1 and -0.5 standard deviations away from the mean? So what's the probability of landing between -1 and -0.5 standard deviations away from the mean? Go ahead and answer when you think you know. 15%. I agree, because that's the area right there. 15% or 0.15. I'm happy to accept either, right? Because probabilities are what? Visually. They're areas. Probabilities are areas. Okay. I'm going to skip the next one, which is similar, but now asks you about anything less than -0.05. All right, so you would start here and you would add all of these areas up, and that would be that probability. The more interesting question, I'm going to retype it up with annotations, but I need to see what it is first, is we can use this for any normal distribution, because we can ask how many standard deviations away am I? So this question says, average time it takes for a novelist to write a book is 800 hours. So if I were to change this picture, what would I change on this picture? I would change it, exactly, I would change a 0 to an 800, right? Because that's my new mean. I don't know if I can make it. I'm going to put it up here so it's a little easier to see. There we go. All right, and the standard deviation, oh, it's going to float with us. Fun. The standard deviation is 90 hours. So if I know the standard deviation is 90 hours, what should I change on here? Yeah, so it'd be, would it be 90 or would it be 90 more? 90 more, which I knew you knew, but just to make sure everybody else is following your thought process. Right. Now one standard deviation is 90 more, so instead of going from 0 to 1, I'm going from 800 to 890. And here it would be 800 minus 90, which, lucky for you, if it's my kind of day for you as well, that's not a big, oops, I put it in the wrong spot. You'll have your calculators if you need them on the quiz, 7 and 10. And now I can ask all the same questions, but about something I might actually care about, which is how long it takes a novelist to write a book. So my question for you is, hours, not minutes. What is the probability that a novelist takes between 890 and 980 hours to write a book? It'll take a few minutes. There's your picture. It's not fully annotated, but it'll get you going, and see if you can come up with an answer for that. Feel free. All right, so the probability that a novelist takes between 890 and 980 hours to write a book. This is a question about probability. So in terms of a picture, it's a question about what? Area, right? And what are the boundaries on the area I'm looking for? Yeah, so I come over here and I find the 890, and then I figure out where should the 980 be. And I believe it's going to be right about there, right, which is 2 standard deviations away. And then I need the area in between, so it's all of this. So it's going to be 9.2. I'm going to convert it to decimals just to continue emphasizing how decimals, that's not right, there we go, are used in probability. And so that's going to be 0. Thank you. Thank you for people who are good with doing mental arithmetic. All right. That's good too. Good for people who bring the right tools with them. 13.6% or 0.136, right? So yeah, someone shows up on your door and said, took me 900 hours to write that book. You're like, okay, yeah, well, you know, about 1/8 of writers are going to be in that range. All right. And so that's how you could use this to ask questions about an individual novelist, right? Because this is the probability distribution for a random variable x. But now let's introduce the central limit theorem. Here's x. If I took a sample and found a sample average for the writers, what do you think that sample average would be close to? 800, because it's going to be close to the average of any individual observation. But do you think it would be spread out as much? No, because it's a sample, and samples have more data, and more data gives you better estimates. They narrow down how much the spread is. So I'm going to have to erase all this, or it's going to get really confusing. I'm going to change that. I'll leave the 800. Why am I leaving the 800 when we're talking about a sample instead of a single observation? It's because it's still the expected value. Yeah. So now I'm going to say, suppose you got 64 novelists. Their average time was 152 minutes. And the sample had a standard deviation of 160 minutes. So we can still use our normal distribution ideas, but we have to build our normal distribution very carefully. So I'll go up and I'll put this information in there, okay? I have it here if I need. Good. All right, so we had a sample where n was 64 and x bar was 752. Notice it's not very far away from the mean, but we're not talking about a single author with 752 hours. This is a whole group of 64 authors where the standard deviation is 160 minutes. This is not x bar, this is of x itself. So if we want to have a distribution about x bar, we still get to use the expected value of x bar is still 800. But the standard deviation of x bar is not 160. What is it? Over the square root of 64, right? It's the standard deviation of your variable, but you shrink it by the square root of your sample size, because the bigger the sample, the smaller the spread is going to be, which is 160 divided by 8, which is 20. That means our x bar normal distribution is not going to have step sizes of 90. It's going to have step sizes of 20. So this point here is now 760. Nope, 780, sorry. And this point here is 760. So where is our 752 going to fall? Somewhere down here. So let me ask you a question. If you collected a sample whose sample mean was this far away on a normal distribution, do you think that sample is representative of the whole population? No, because the probability of seeing something that extreme or more extreme, even if I do both sides, I'm at least that far, right? The probability is very small. So the probability of observing more extreme than 752 is less than the cutoff. And if we don't have any other cutoff given to us, we let use 0.05. And that tells us that this sample is probably not representative. I'd be surprised to see it. It's interesting in some way. Sorry, I can't move that. Let me write it again. Probability of observing more extreme than 752 is less than 0.05. So it's likely not representative, probably not representative. So there's something interesting about it. And we go and we find, oh, these are romance novelists. Romance novelists write their novels very fast. All right, whether you like the romance novels or not, that's what I'm saying, but they tend to use a formula, helps them write them a little bit faster. And you say, aha, I knew it was worth looking into deeper. There was something interesting about this group. And now my research has shown me what it was. Practice with this. You get to practice on your lab. All of you are given a continuous variable where you're asked about a single individual and then a sample, right? Where the number is the same, but the single individual, maybe not surprising, the sample maybe is surprising. And you've got some practice here, and you've got some practice on your homework, and you will get some practice on the quiz. Any last questions about this idea? Okay. Now we get to use this tool because whether or not the underlying distribution is normal, the sample means are distributed normally. Yeah, question.
The middle, would you say that it is representative? Like, where's that threshold exactly at?
Good question. What's the threshold? What's the cutoff in terms of number of steps where we say something is surprising or not surprising? And so in terms of steps in a normal distribution, it's basically exactly 2. Yeah, it's just a little bit less than 5%. So you could stop short of 2, but let's use 2. You don't have to be exactly right. Yep. The nice thing about the normal distribution is instead of thinking about areas, you get to think about steps of your standard deviation, which, by the way, is a great question because that's also on your study guide. Way at the bottom. Why do we use 2 standard deviations if we're not told otherwise from many different statistical analyses? It's because in a normal distribution, that represents 95% of the probability or the data. And anything beyond that is surprising. Okay. Let me point out one more time what we use this curve for. We already had a normal distribution, and we used it to ask questions about a sample. We can also use a sample to ask questions about a population. And so that is what confidence interval is. So let me give you an example. So we're moving into confidence intervals now. suppose you collect a sample of 50 cats and you did a pretty good job with your methodology. You think it's a pretty random representative sample. And that sample has an average weight of 50 pounds. My question for you is, based on that, what do you think the average weight of all cats is? If you have an idea, you can say it. Probably 10 pounds. That's what our data said. We're statisticians. We use our data to understand systems, right? It's a statistics is a science of using data to understand systems. So let's use our data. Yeah, probably 10 pounds, because that's what our data says. Not only that, one of the things that's nice is the central limit theorem says the expected value of our mean is also the expected value of our variable. So a sample mean is usually the best estimate of a population mean. And this is one of the places where statistics really got started, because in order to understand a population, those are too big. So we study samples, but it's only worth studying a sample if it's going to tell us something about the population. What was I going to say? It was probably important, but I don't remember. Do you think that the average weight of cats is exactly 10 pounds? No, why not? You never expect to be exactly right in statistics. So I don't think this sample is going to give me a perfect estimate, right? So it's usually the best estimate. I remember what I was going to say, but it's not going to be perfect. So what does it mean to be the best estimate? Reasonably close. That's a judgment call for sure. And as long as you're collecting your data well, unbiased. It might be a little high, it might be a little low, but it's not always going to be high. It's not always going to be low. And as Gabby and I talked about, the sample mean is probably not exactly the population mean. It's probably reasonably close, because you never expect to be exactly right in statistics. So in addition to having a best estimate, it would also be a good idea to give a reasonable range. I'm going to give you a couple options for this example. Do we think the average weight of cats is between 8 and 12 pounds? How about between 0 and 20 pounds? Between 9.9 and 10.1 pounds? Or between 9.5 and 12.5 pounds? So take a minute, read through those, think, is one of these ranges the most reasonable? Everybody sometimes. So which of these is the most reasonable range according to the fact that we have some scientific knowledge behind this? A, yeah. Why did you say A is the most reasonable? Yeah, I mean, yeah, Gabby?
Very, very small. And then D is like a weird spread. It goes down 0.5 and it goes up 2.
Yeah. So thank you for the more detail. And what you did was you did a comparison. So um, last one standing is always a good choice, right? It is hard to say why we think this is the most reasonable. And that's one reason we use statistics is so we can put some numbers behind our decision. But yeah, I mean, first of all, 10's in the middle because it's supposed to be, and it's supposed to be reasonably close. So it could be off by about 2. That seems reasonable to me. Now, as Ryan pointed out, well, if 8 and 12 is a possible range, 0 and 20 sure is. But is that very reasonable? It's not very useful, right? Reasonable means a lot of things. One is I could believe it, but 2, it's also useful. I could always say the range is between 0 and 100 pounds. Nobody owns a pet cat over 100 pounds, so I can be certain the average weight is not over 100. But that's not useful at all. It's got to be useful in order to be reasonable. So this is too wide to be useful. And this is too narrow to be believed. I don't think I was that accurate with my data. I know this handwriting is super small. And this one's not centered. So it doesn't really make a lot of sense not to center, at least for the mean. There actually are some statistics where your confidence interval isn't centered, which is interesting, but not the ones we're going to be looking at. So this one makes the most sense because it's centered on our best guess and it doesn't seem too high or too low. But let's use some statistics to help us pick the actual endpoints of our interval, to help us pick the reasonable range. It should be a reasonable range and it should balance narrow enough to be useful, wide enough to be believed, or to have confidence in it, which is why we call it a confidence interval. So for that, we need a little more data. We need both the mean, the sample mean, X bar, which was 10. Please focus. We need the sample size, which was 50. And we need some way to see how spread out that sample was. Because if our sample had cats that weighed as little as 5 pounds and as much as 15, we would have less confidence in our estimate than if all of our cats were either 9 to 11 pounds. So we need some number that describes the spread of our sample. Anybody? I'm really sorry about the focus thing. It's driving me crazy. We need a single number that could describe the spread of our sample. Anybody think of a single number that describes the spread of data? Let's use a standard deviation. because we can calculate it. We can't when we don't have the data, but let me tell you, for example, that the standard deviation was, let's see, 3, right? So we saw some cats that were as light as 4 pounds, some cats were as heavy as 16, maybe even a little more than that, right? So with this information, we know not only where is that sample centered, but also how much it's spread out. And then we combine that with the central limit theorem to estimate a range for the population mean. Statistics is a mathematical science, and so here we're using the mathematical part of the central limit theorem to help us. Our best guess is a sample mean X bar, 10. If we're thinking in terms of standard deviations, how many standard deviations away from our mean do you think is reasonable? Say that a little louder, Aspen. 2. Right? And nobody tells you otherwise. 2. So let's take 2 standard deviations. But we have to be careful. It's not standard deviations of the sample because we're looking at a sample mean. So we need 2 standard deviations of the sample mean above and below the sample mean. And again, this is the part that can be really confusing, is when do I use a standard deviation of a sample or a population versus when do I use a standard deviation of a sample mean? This is one of those cases, anytime you're going to use a central limit theorem, you're talking about the sample means and not individual observations. So we need the standard deviation of X bar, which is 3 divided by the square root of 50. Because it's the standard deviation of an observation or the population divided by the square root of the sample size. That's 0.42 approximately, which is very small. Why is it so small? We're talking about cat weight here, right? Less than half a pound for a standard deviation. Why is it so small? It's because we're not talking about an individual cat. We've stabilized our estimate with 50 observations, right? That's going to stabilize us very close to what the actual mean probably is. So it shrinks how much we think we'd be off by. So my best guess, I'm just going to keep writing it. X bar is 10, and my reasonable range is going to be 10 plus 2 times 0.42 and 10 minus 2 times 0.42, which is 10.84 at the upper end and 9.16 at the lower end. And to put this in a conclusion, we would say my data indicates that the average weight of cats is between, let me start at the lower end, 9.16 pounds, and 10.84 pounds. That's a pretty narrow range because we collected a lot of observations. And again, it shows the power of collecting data. If we just picked one cat, we could still say, I think that's probably what the average weight is, but we would have no confidence in that guess. Which brings me to that keyword I just said, confidence. How confident are we that we're correct here? Very confident. We can put a number on how confident we are. And the number comes from the choice of two standard deviations. How much of a normal distribution is within two standard deviations? 95%. So two standard deviations corresponds to 95% confidence in our range. If nobody tells you otherwise, we use a 95% confidence interval. We could use a 90% confidence interval. We could use a 99% confidence interval. We would pick a different number of steps. All right, so I'll do another example. The best way to practice this is to actually have some data to work with. And so in the labs, you're going to be doing this based on your data. But when a teacher or a problem set comes up with an example, it can take time to write down 30 different observations. So we usually just tell you what the mean was, tell you what the standard deviation was, tell you what the sample size was, and you go from there. So the average temperature on May 7 in a random sample of 36 different years was 65 degrees with a sample standard deviation of 12 degrees. Right? So you could have some real hot days, you could have some real cold days. Oh, I don't want to use 12, sorry. Let's use 18. Whenever you create a question, you want to try to avoid numbers that cause confusion. And if I had picked 12, we would have ended up with some potential confusion. So let's build a 95% confidence interval for the average temperature on May 7th. I wanted to walk through the thought process, but now I'm going to get a little more formal. And confidence interval, abbreviated CI, the way I teach it, has three elements or three pieces. It has a best guess, it has a reasonable range, and it has the confidence level itself. How confident are you? So any confidence interval should have a best guess, because if you're not giving a best guess, you're not giving them whoever needs that information as much as you could. A lot of times, confidence intervals ignore the best guess part and just do the range and the level. But I think it's helpful to have the best guess also. In this example, what is our best guess? 65 degrees because it was our sample mean. Your best guess is always your sample mean. For the reasonable range, we have to do a little more work. Okay, so if nobody tells me otherwise, I'm going to choose 95% for my confidence level because that's what humanity and science has generally accepted or decided on as what we want for confidence and probability cutoffs, et cetera. This tells me to use 2 standard deviations of the mean, of the sample mean, when building the range. So the standard deviation, how much I would expect my sample means to vary, is going to be the standard deviation of the sample divided by the square root of the sample size, which is, let's see, was 18 over the square root of 36, which is 18 over 6, which is 3 degrees. And from this, I build my reasonable range. It's going to be, I'll use interval notation here because we use that a lot. It's going to be the sample mean minus 2 standard deviations of the sample mean up to the sample mean plus 2 standard deviations of the sample mean. I'm going to write it again. Now maybe you see why statisticians started picking letters and X with a bar on top, right? It's a trade-off. It would be a lot more compact if I used notation. And in this case, that's going to be 65 minus 2 times 3 up to 65 plus 2 times 3, which is 59 degrees up to 71 degrees. So to put this in a sentence that a non-statistician might appreciate, my best guess for the average temp on May 7 is 65 degrees, and I am 95% confident or sure that it is between 59 degrees and 71 degrees. And now we know more about the system than we used to. Now we can actually start to understand how this system itself works. Okay, I got a couple more things I want to say about this. Even though we are, going a little bit long because I talked a little about normal distributions otherwise, but bear with me. Okay, so first of all, I wanted to be more confident about my range, more confident that the range actually does contain the average. What could I do?
Change your confidence level.
Yeah, I could say I want a bigger confidence level. What would that do to the size of the range? Let's go back to the cat example. Are we pretty sure 8 pounds to 12 pounds contains the actual average range? Are we more sure or less sure that 80 to 20 contains it? We're more sure because there's no chance it doesn't. Are we more sure or less sure that this really little interval contains it? Less sure. So if you want to increase your confidence level, you have to increase the size of the interval. Because you have to make it less likely that you got it wrong. How sure are you that the true temperature is between 5 degrees Fahrenheit and 200 degrees Fahrenheit? Basically 100% sure, super wide interval. How sure are you that the true temperature is between 66 degrees and 68 degrees, 65 and 67, sorry. Not very sure because that's a very tiny interval, right? So more confidence requires a wider interval. Less confidence allows you to have a smaller interval. And you get to choose. You get to say which is the best for my purposes. Generally, we accept that 2 standard deviations, 95% confidence is useful. There's something else we could do to be more confident about the range. Think back to the rules of 3. If you want to improve your statistics, you can always, yeah, or collect more data. This will increase confidence without making the interval wider. Mathematically, that works out. But logically, that should also make sense. If I have more data, I get more accurate estimate. So I can be more confident in my range. Okay. 2 other things I want to say. So the reasonable range, which is x bar minus usually 2, not always 2, two times the standard deviation of x bar and x bar plus 2 times the standard deviation of x bar. This 2 times the standard deviation of x bar is referred to as the margin of error. In particular, it's a 95% or 5%, 95% confidence margin of error. So when you see anything reported in the media and they take confidence or a margin of error of plus or minus, they're talking about this. Now, what's confusing is often they report it as a percent, plus or minus 3%, but that's a different percentage here. That's what percent of people support this candidate. 48% of them plus or minus 3%. They're talking about this margin of error right here. That's just a phrase I want you to know. And then the last piece for today is there's a problem. With this method. The central limit theorem requires knowing about the population. The central limit theorem says if we know the population expected value and the population standard deviation, we can use that. But when you collect data on a sample, we don't know about the population. If we did, we wouldn't have to do this. Right? If we knew what the average weight of all cats was, we don't have to estimate it. Confidence intervals are useful only if we don't already know about the population. So our sample data is probably a little wrong. Not only the sample mean is probably not exactly the expected value, our sample standard deviation is probably not exactly what it should be. To fix this, we could penalize ourselves and choose a slightly wider interval. The technical way to do this, and I'm telling you this mostly because you might see it in the future. For me, and honestly for most statisticians, this is not an issue that we deal with in practice. Instead of using a normal distribution, we use a penalized distribution called a t distribution. The upshot is if you have a small sample, you have to use a wider confidence interval. If you have a big sample, you're so close to the normal distribution anyway, you don't have to really adjust. In practice, n at least 30 gets you so close, or I should say close enough, to normal, so we don't have to worry about it. If you don't have 30 observations, you have two choices. One is collect more data, or two is use something different instead of this process. And if you take 244 with me, you'll see what that difference process is. It uses simulation. So I did want to put that out there. In your textbook, you're going to see this thing about a t distribution and how you have to use that instead of a normal distribution. Basically, what it means is the true value for 95% with a normal distribution is 1.96 instead of 2. And the true value for a t distribution with 30 observations is about 2.02. They're both really close to 2. Let's just use 2. All right, that wraps it up.